Hello guys, you can hear me, right? Okay. All right, 7 o'clock. Let's get started. All right, today is a review on lecture 10 until 7:40, 7:45. And then 8 o'clock, I will do the recitation number 5. That will be the last recitation online. And after that, we will be having recitations face to face in campus. Okay, for lecture 10, it's implementing data structures. So basically, we have many representation for the same thing. So in this particular lecture, you see different kind of data structure. We actually open up the hook for you to see what are the things that you can do to implement your own data structures. Uh, we show you about sets, we show you about complex numbers, and actually both of these are already data structures available to you in sort of primitive way in Python. But still, we implemented them for you to see. And of course, some of the programming languages, they may not have this set, may not have this complex number. Then in that case, you would have to do what we do in our lectures to implement them yourself. Okay, so for the case of complex number, there is this Cartesian coordinate systems and versus the polar coordinate as for different kind of usage or different ways. Okay, the first question is why multiple representations? Today's review, in some sense, I'm trying to relate you, bring you to pretty much in real life. A lot of the things that we do in real life are actually happening in computer science or in computer per se. And why is that so? We should notice that often enough because a computer is actually executing very fast, but ultimately it is still trying to automate what we human know how to do in a particular fast manner, and we tend to forget about that we thought that computer is superior to us. Actually, it is not the case. After all, you are the one who designed the algorithms to ask the computer to execute. Okay, even though in the AI realm, actually the AI area, a lot of the things are in some sense learn and remember, but they are actually in some form of data stored, and then you're just pulling out data with some kind of probability that given to all the data. All right. Here is a picture of different kind of knives. There are knives to cut bread, and there are knives to cut meat, and so on. There are various. So you can see that even in kitchen, there are all these different things, but they are also for one purpose, is to cut something. All right. But it depends on the something that you have to use the different types for efficiency purpose. All right. So having multiple representation is that each representation is good for a different purpose. So a knife are represented in different manners or different shape, different ways of the handle to be able uh, to make the force on some of these edge. All right. It's same also that you see dishes. Dishes like 宫保鸡丁. If Chinese, you know, this is a chicken dish. But it's depending on the purpose. This could be a vegetarian dish, also called 宫保鸡丁. Or in the normal a non-vegetarian style, this is actually a meat dish. All right. So if it is served in a vegetarian dish, it's meant for vegetarian. All right. So it's the same name, but yet it is for a different purpose. Now there are two situations actually what we deal with in computer. All right, we can if you have multiple representation, then you can use the various representations. Like in the case of the complex number, you have the Cartesian and you have the polar. All right, so they are indeed in that case you can use either one of them, or you can pick one to be used. If you don't want both of them in your system, and then you are just using one particular representations. But in this case, there are still various ways that you could implement the representation. All right, when I talk about that, I meant that we create the complex number ourselves. All right, in the case of Python, actually, complex number is a primitive data type that you can use directly without creating it. But for other languages, maybe you would have to create it, and then there would be various ways of creating it. All right, so we do such a thing. It's after all, in computer, here we are talking about time and space. Okay, and these are in time and space are in relation to the resources. And so what we want is efficiency. We don't want to wait for a long time to get our answers. So we want to be able to do things fast. But on the other, because we have multiple representations, then we possibly can adapt to using this or that you can achieve efficiency as you wanted it. I remember this very clearly that in matrix in mathematics, if you don't represent a matrix properly or correctly for your purpose, you actually will incur n cube time complexity. On the other hand, if you use a linked list, you can actually get it down to depending on the content of your matrix. In engineering, there are lots of the time that most of the entries in a matrix is zeros. And so to such a case, and you choose the correct representations, you are actually gaining a lot from n cube time, could bring it down to n linear to the number of non-zero entries. Things like this can happen. All right, but there is no free lunch as it's stated here. So when you have multiple representations, you have to pay for these multiple representations also. All right, here are the prompts. All right, first of all, if you have redundancies of representation, means that you have multiple way to represent the same thing, then you would have to maintain consistency. All right, because oh no, after all, this is about a fact. You cannot be saying that it is true here and then the other representation say it is false. All right, this is the most obvious one. And also, of course, this representative cannot give you number 10 and then the other representative give you number 10.1. All right, that it's also not acceptable, even though that it is only a difference of 0.1. Okay, you have to maintain consistency. Okay, so while this thing happen, and you sometimes allowed to have temporarily inconsistency that you can afford it, and in some of these applications, what I have is in mind is this. For example, nowadays all our web pages, all right, yours, mine, and so on, they are not just stored in one place in your computer systems. Actually, it is stored around the world in the different nodes because they are cached there, meaning that you can other people wanting to get your web page, it doesn't need to come all the way to Singapore to or maybe in SingNet to get your web page, or in NUS to get your web page, because some of these web pages are actually duplicated in some other places in the US or in Europe and so on. All right, so when anyone wanted to get to see your web page, for those guys in Europe, they will access to the European the server to get it, and there's no issue about that. But there is a possibility that of course, when you have all these multiple web pages around the world, you would have to also somebody would have to maintain the consistency for you. But you are not the one who make this inconsistency because you only created one. It's just that the World Wide Web is such that the system some mechanism is there to make copies of your web page in various places in the world. All right, and as a result, so when you, for example, you update your web page that you're no longer in NS, but you're now in NUS, and that kind of update may not be propagated immediately to all the other copies of the web pages. Those other copies are the different multiple representations of yourself. But this is okay because there's no harm, right? Somebody who got the message in Europe may get it at you are still in NS, but who care, right? That temporary consistency in such kind of situation is tolerable. Okay, it's not going to be critical in any way. But on the other hand, if you are making duplicate representations of financial data, right, you save money in Singapore with this amount, and then there's a copy of the amount that you save in New York, and so this copy must always be consistent, all right? Yeah, yeah, and it cannot be even different by 1 cent. Okay, financial accounting will not allow that. Right. So for such kind of situation, multiple representation would need some mechanism to be able to make sure all copies of the data are consistent as much as possible, instantaneously consistent in some sense. All right. For that to happen, there are mechanisms in computer science to allow you to lock the data without and not allowing anyone to access it until the record is fully updated. Then it can be released, and all copies will be made available. All right, the New York copy and the local copy. Okay, something like that. All right. So this is the problem of managing the redundancy of representation. Okay, and of course, if you have multiple representation, the end user who is using your representation, well, we may have to know which copy. Hopefully not actually, because if you have to know where to get the data, then it will be tricky, become very confusing. It will be difficult to use the systems. So fortunately, all computer systems are such that they are all developed in a layer manner. Okay, so if you need a particular information, you are asking it through usually what we call the API, application programming interface, all right, to be able to get what you want. And you are actually getting it through one layer of the interface to you. And here I stated that actually most of the computer systems, or in fact, a good computer systems will be designed such that they are all layer, and you are only asking from your layer 5, you're only asking for layer 4, things from layer 4, if you are staying in layer 5. All right, likewise, if you are staying in layer 4, you are asking for layer 3 and so on. Okay, you will not be asking for layer 2 if you are at layer 4. All right, something like this. So this is counteracting to making to the user that there is no confusion, basically, that you can actually rely on or API to make access to the system. So for example, in our notes that you have complex number and Cartesian coordinate versus polar coordinate. But you don't care. When you ask for angle, even though you are in which will be directly available from polar coordinate, it's not available from the Cartesian coordinate, but there is a function in there that will give you the angle, all right, by taking the x divided by taking the y divided by the x, okay, and tangent it, okay, to get the angle. Right, so whichever representations, all these API will unify the way that you can access to the data. Okay, so these are the problems and there are some solutions to handle them. The next thing is that All right. So how do we know which is the good representations? All right. For example, should you be using Cartesian coordinate or should you be using polar coordinate? So the API is what you use actually, and you do not know which one that the system will channel you to use. Okay. And most of the time, these are things the whoever designed this system these complex systems, complex number systems, can then build in something to capture statistics. All right, they capture the statistics to know that which is the most frequently used functionality or so on. And then with that, okay, and either using the real data to know that which is the functionality that's being used, or you can do some simulations as what we talk about, or you can use some mathematical analysis to analyze things and to know that which actually is the data representation that is most likely most used, and then you can then channel all the requests using that, and you make efficient those data processing in that representation. Okay, so this when it come to usage, we study the past history to learn about the statistic and do the appropriate redirections or redo to the correct data structure. Number two, do the same operation, searching at the same time. This is what Google does. So when you do a search in the Google to the box, you actually immediately you are sent to do there is this thing Hadoop to be able to process all these at the same time, and whoever come back with the answer will be the one that presented to you. Okay, and that it's also possible. Or you use some mathematical analysis to argue which is good, and we use it. All right. And for sorting that you saw in lecture 9, this is there are some parallel processing thing that except that computer cannot see more than two elements at the same time. Okay, that is when we do in the CPU, we actually compare two numbers at a time. We don't, there's, unless there is a CPU instruction to allow you to do multiple comparisons, but generally this is not the case. All right, and you can do parallel processing, but you cannot do more than two element comparisons. Okay. Now, all in all that I've talked about here, it's that this has been the goal for the human being. You want to, of course, I don't know whether this is a good or the bad thing. There's still a lot of debate on this, the AI stuff, right? The AI, it's whatever artificial intelligence or large language model that you see these days, they are actually trying to mimic the human being. So in some sense, there is mimicking the human being to the extreme, right? So while we are talking about all these things, we are actually only mimicking certain scenario in the real life in computer. But AI is taking this even to the next level, right? And trying to do everything as if it's like a human being. Okay, but you can see that this is the ultimate goal in some sense. Some people are afraid, and I don't know. So this one is still subject to the history to tell us. Okay, and this is the part about the multiple representations. Basically, I wanted to tell you that these are some of the background that you should know when you're studying these things. And we are actually opening up the hook for you to see the implementation. Of course, we need not do that, and then we will just be blindly applying what you can use. For example, set and complex number. I mentioned this many times. They are already available in Python. You could have used it directly, but having them, having you seeing the actual implementation, that helps you in the future when, for example, a particular language may not provide you with set, and then what to do? You can actually implement it yourself, right? And in the case of many other languages, actually dictionary is not available, but it is in Python, and it's very useful. And so, but you can build a dictionary yourself actually. Okay, so we actually make things at this level of study is not that you just take what we say. Just like just now, I was answering to uh, Ray Young, said no, not everything in Google it's going to be the truth. Right? Some hallucination is there, and they will just may guess some of the stuff which are actually wrong. All right, so don't believe everything there. Okay. So you have to know how things are fundamentally why there are things done there. Okay, in the next 20 minutes or so, I'm going to show you some examples of what computer we implemented things in computer which actually we learned in real life. Okay, so there are many similarity in real life that we actually took them and implement them in computer. Okay, and we tend to forget about this because computer is so fast that we then didn't realize that actually this is what we have been also using, and the only difference I guess is that there are a lot of mathematics that in computer science that there are lots of mathematics that in use in computer science to explain why certain thing it's actually good. All right. Of course, anything that's bad, of course, there's nothing to explain. Okay. So usually math is used to explain why something is good. So I'm going to share with you two examples. There is another example that I remove it for today because I want to reserve that for next week when I have another chance to talk to you before the midterm. All right. So the first thing I wanted to share with you is that here is a common thing that we do. All right. Suppose you have a class of 40 students, and we are supposed to clean up the classroom every day. Okay. Of course, for example, mopping the table, mopping the whiteboard, and putting all the rulers or whatever properly, and so on, sweep the floor, and so on. All right. So there are two ways to do this. Okay, because there are 40 of you. All right. So how are the two ways? So one way is that everybody spend 15 minutes every day. Okay, that it's a possibility, right? So everyone just stay back after class and do it for 15 minutes and then you can go home. All right. Another way, it's kind of like, okay, we will take turn, right? We make it into 20 pairs of 40 students, right? And there are usually 20 working days in a month. Of course, you can, this agak-agak, this usually is 20 to 23 days in a month, okay, working day. And so if you have that many pairs, each one will just do one duty per month. All right. Of course, there are only two of you, so you will have to spend more time, not just 15 minutes, but maybe 1 hour, okay, 60 minutes. That should be more than enough. 1 hour to clear. Then why is this one need 15 minutes? Because the more people doesn't mean that they will be faster because there will be lots of communications. Some people lazy around and not doing anything, and some may do it wrongly, and then somebody else has to correct it, and so on. All right. So this 15 minutes is because just like when there are too many people, also may not be necessarily the good thing to do certain thing. All right. What is which one is better? Okay. The first case is clear uh that in a month of 20, each person takes 15 minutes. So you spend a person will spend 300 minutes, which is about 5 hours. Okay. On the other hand, the second case is that each person is rotated to do it once a month, and therefore it's 1 hour only. So you can imagine. So instead of all of us spend 5 hours to do the job, now we only spend 1 hour per person to do the job. So if you take this 1 hour per person divided by 20, each one it's only about 3 minutes. Okay. Each day you will basically accumulate 3 minutes to do the job. All right. So this is the kind of thing that happening that the first case is that everybody get busy all the time. The second case is that we don't get busy all the time. We lazy around. Only once in a blue moon, we become busy. Okay, so actually once in a month, we become busy in the second case. All right, so when in the second case, actually it's what we call the amortized case. All right. So we in the lecture on the sorting, you saw worst case, meaning that what is the worst input that it could happen to a particular sorting method. For example, the bubble sort. If you reverse the array, you reverse the array, you or actually not, but still okay, so worst case in the case of bubble sort would then be that you have n square time, you pay n square time. A good case is that if you have the bubble sort, but the bubble sort given is the input is sorted, and then in this case you just run through the list one time and then you can stop. So in this good case is linear time on, all right, whereas in the worst case is on square. In the average case, when we talk about all kind of inputs, with probability for each type of input, usually you give uniform probability. Then you just average out the cost, and this will usually be random. For example, you take a random input that will be giving you the average case, and this is again for bubble sort, it's going to be n squared. All right, so these are three terms, worst case, good case, and average case. And there's this new term called amortized case. All right, there's no assumption on the input. Right, we don't mind occasional working hard once a month, but we often relaxing. Uh, so amortized case is such that you uh, you are you are not doing much work most of the time. This will not be pertaining to sorting. This is pertaining to the example I'm going to give you shortly. All right, it's you most of the time you only very fast, you can do it very fast, but once in a while you have to do a lot of work. Okay, but average out the amortized cost is still very low. All right, so that it's amortization. Amortization means that you spread out the basically here is the definition. All right, take into account a sequence of operation. This sequence of operations, which is whatever the sequence is, meaning that there's no restriction on how this sequence come about, and the amortized cost is just the total cost that you need to pay for all the operation divided by the number of operations. All right, so for each operation, you sometimes pay one operate cost of one. Sometimes you pay cost of n, all right? Sometimes you pay, and most of the time you pay cost of one. So when you average it out, you actually still pay cost of one, all right, constant. Okay, here's the example I'm going to give you. Okay, this is a real thing in happening in computer memory. So, right, in the memory management, okay, because whenever you wanting to get a list or what happened is that you ask this, you know that list allowed you to keep appending until as long as you want, okay? But it is not the case that the memory management, I mean that the operating systems in the computer, it's giving you everything in the whole world in the computer to give it to you. Actually, it's very conservative. It only gives you to, for example, 16 slots. 16 is just an example, which is good enough example for our purpose. So when you first request for storage to store a list, okay, the computer system may give you 16 slots to put things, okay. And this 16 slots, of course, then allowed you to put up to 16 items. Okay. Assuming that all items are the same in just numbers. All right. Of course, if you have other data type, then you will be done in a different manner. All right. So you have 16 slots to put 16 items, 16 numbers, for example. Okay. Now, when you add one, you start using the list, you add an item, add another item until you add until 16 items. Now, at this moment, everything is filled up. Okay, all the memory is taken up already. So when the 17 items comes in, the system cannot put it into the originally allocated 16 slot anymore. So what does the system do? The system will have to allocate you 32 slots. All right, this is what happened. This is the doubling thing from 16 to 32. Okay, so the system will then give you 32 slots. And in the case of Python, you may not have seen it because we checked before the ID. Actually, the ID never changed all the time. But if you add long enough, I believe at some point maybe the ID will change. Anyway, for when you have 32 slots, assuming these 32 slots now at the different locations from your original 16 slots. Okay, so you are taking the 16 slots and then now you're going into the 32 slot. What do you have to do? Of course, you have to copy all your 16 slots, the content in there, into the newly allocated 32 slots. All right, to occupy the first 16 slots. At the same time, also add in the number 17 slots the number 17 items. Okay, so this is what happened. So when you are doing things within the 16 slots, yeah, you are happily at one. You pay one cost to add the item. All right, or one. But when you hit number 17, actually behind your back, actually the system has to copy out the 16 slot and into the new 32 slots at the same time to add the number 17. So at this moment, when you see this, it actually means that you are doing a lot of work now. This is the occasion that just happened. This is the situation where you were happy-go-lucky all the time here, spending only one unit to copy to append. But now, when you're adding the number 17, you are actually copying the 16 plus the number 17. All right, so you actually have to wait a little bit, even though you didn't know. Okay. Likewise, when you use up all your 32 slots, you have to go into 64 slots. At this moment, when the system gives you 64 slots, you are actually copying the 32 slots into this 64 slot and then add in the number 33, 33rd items into the slot. All right, and so on. When the 64 slot is used up, you have to copy them into the 128 slot and so on. All right, so what happened is that each time you double and you spend effort to copy two. Okay, when you double it. All right, so how costly is this approach? All right. You're happy often, but you need a lot of effort once in a while. How often is once in a while that is causing you trouble? Here is the calculation. The calculation tells you that your amortized cost it's only O3. O3 is actually O1. Basically, so the amortized cost is that this is per operation, each append, all right? The append is adding in an item. You are only paying 3 units. This is what this argument is going to tell you. So how does the argument go? So this is the mathematics part of things that I'm talking about. So we are given 3 units for each append. Basically, you claim 3, you already pay 3 for each append. Although an append, most of the time you only use 1 unit, correct? Because you only add in 1 item to the list. But this is what quite going to happen. How do I going to use these 3 units? At the moment that when the number 17 item comes about, we also pay him 3 units. And this 17th item is going to pay this 1 unit on its actual items. It pays the 1 unit on the actual append, keep 1 unit, and then give 1 unit to the first item. Okay, so basically I charge each. This is the calculations that are usually done to amortize analysis. So basically, the counting, the counting is upfront. They give credits to each operations, and you will see that you never get into deficit. Basically, all the credit given to you, it's good enough to pay for every operation that you need. Therefore, the the credit that you give is indeed the amortization cost per operations. All right, in this particular example, the amortized cost is actually credit of 3 units. All right, so how is these 3 units being spent? It's why this thing goes through with just 3 units. All right, when you're at the 17 item to be added, you basically you are given 17 the item pay for 1 unit actual append, keep 1 unit, and then and also give 1 unit to first item. Okay. At this moment, I didn't talk about actually the copying of the 16 items before the number 17. This happened when we hit 32. Okay. Of course, you can also argue it for the previous case. So I'm arguing for the following case. Okay. Then when the number 18 item come along, you also pay 3 units, use 1 unit, keep 1 unit for yourself, and give 1 unit to the second item, and so on. So that is to say that number 19 items come along, number 19 item come along, also given 3 units. 1 unit is kept, 1 unit is used up, and 1 unit is given to the third item, all right, and so on. By the time you hit 32 units, all right, you would have given everyone from number 1 to number 16 1 unit, yourself on the 17 to number 32 1 unit. So everybody has money, have 1 credit. All right. So when you move yourself to 64 items, you will use this 1 unit to spend in the copying. So basically, when you move from 32 units to 64 unit, you are actually paying using the saving that you have 1 unit to pay for the copying. That is to say that whatever operations that incurred by doing this transferring from 32 to 64 slots, you already accounted for because everyone has 1 unit spare. Okay. And as such, if you keep repeating this thing, you never run out of money. Everybody has at least 1 unit or 0 unit, never get into negative. And therefore, every operation by attaching 3 units, it's good enough. And as such, the amortized cost is 3 units, okay, which is O of 1. All right, so this is O of 1 means it's constant, so you never have to worry about it that you more than you're paying O of n per operation, because nobody will see that in the amortized sense. All the time you are always in constant storage, constant expense of the credit. All right, so this is a simple example of the amortized analysis, actually. So you learn about worst case analysis is to give you example. Good case analysis is also give you an example. Average case analysis is not just example. Maybe you have to use some probability to help you to calculate, do summation, and so on. While amortized analysis is like here, you are giving credit upfront, and then you see that the credit given upfront is more than enough to support all operations upcoming. Operation coming include append, also include copying to the new array. Okay, so this is amortized analysis. There is another example that I talk about, union file data structure. This is even more bizarre and more difficult. I shall leave it to you to, if you are interested, you can see it. But it will not be appropriate to talk about it here. Okay, I have another 10 more minutes. Let me give you another example. Well, I hope you're okay. I don't, these are all, in some sense, giving you some sense about, oh no, there are various kind of analysis, worst case, good case, average case, amortized case. This is easy by giving example. This is easy by giving example. This is not so easy anymore. You need to do probability. This one is also not that easy. This happened to be the easiest one by giving enough credits to everyone and spend the money. Okay, and the next example I want to give you, it's something that I think you should be doing. All right. If you have a bookshelf at home, all right, so you have all your notes that arrange on your shelf. I don't know how it works, but for your case, but usually you may put them in. If the shelf is big enough, you will just move them into different parts by hashing kind of mechanism. All right, or you keep things that are often used near to you. All right, so if you do this, then here is the strategy that is happening in computer. All right, so here is the similar to this bookshelf thing. So suppose you have a list you're searching. The list has number 10, number 20, number 11, number 22, 15, and 18. All right, the strategy you're going to see is called move to the front strategy. All right, so suppose you want to search the list, you want to search for number 22. So what happened is that you search out 10, oh no, this is not what I want. 20, no, this is not what I want. 11, no, this is not. And 22, yes, this is what I want. So once you have found it, all right, of course, all these are key and actually they have associated data. Okay, we will ignore the associated data for now. We just imagine that we are just working with keys. Right, so this 22. So you find the associated information and then you go into your applications to do something about the associated informations. All right, so this is what happened. And the next round, maybe you need to search for 11, right? More then and so on. Of course, you can leave it like that. All right, you can leave your list as it is like that, and then each time you want it, you just go in there and search for it. All right, but if you do that, then somebody bad could come and fool your algorithm. That somebody bad can say, okay, you're going to do this, you always keep this, so you never change, so I'm going to fool you. I'm going to fool you by searching for number 18. Number 18 is at the end, so you have no choice. Pay one cost, pay one cost, pay until 18 you pay. All right, you get the information. Next time round, again, okay, you don't change, right? So I will ask you to search for 18 again. So you can see that this is quite bad, right? Whoever you are looking for is always at the back, right? And you are not flexible, you never do something special, clever about it. So the adversary, and in algorithm design, we call this kind of person adversary, can fool you by making you look bad, okay, basically. Now, so instead of being fooled, here is the strategy about move to the front. So how does it work? So when you have found your number 22, you don't just stay there, you move the 22 to the front. Well, you swap with number 11, so you get this. All right, you swap with your number 11, you get this new list. Then you also don't stay here, you swap with the 20, you get this. All right, the 22 is in front. Then you swap with the 10 to be in front. Okay, so this is how move to the front strategy means. But whenever you have found it, you move into the front. Okay, so suppose this is in the premise that whatever you you found, right, it's likely that you may want to refer to it in the near future. Therefore, it's good to be in front. Just like in your bookshelf, right? So, for example, you have notes for your math, more for your computer science, note for your chemistry, note for your physics, and so on. So you are looking for physics, so you go through and then you found your physics. Usually you will want to, after you refer to it, you don't want to just put it back to the same place. You may want to put it near to you. All right, so the next moment that maybe in the next hour or next few days, you're going to refer to the physics often. So it's good to move it to the front. All right, so this is in the same spirit as that. Okay, so it's mimicking in real life what we do, or it could be that we are lazy, so we take it and then we read it, we just dump it on the table. All right, but that is also means that it's near to you. Okay, so this is the mimicking things like this. So this is in the spirit like the first search just now we did is 22. The next search could be 22, which happened in computer because in computer when this thing was developed during the time of compilations, and when you compare things, you're referring to a particular variable, and that variable, when you refer to it, you want to find out the type, the memory allocation, where it is, and so on. Usually, you're going to the next in the coming few statements, you're also again going to refer to the same guy and therefore it's good to be in the front. Okay, this is in compilation. All right, so now next, if you're searching for 11, okay, this is just example, so I don't mean that what I'm doing anything special, but just you search 22, so you pay when you search for first 22, you pay what? You pay 1, 2, 3, 4. Four comparison to get to him. Then you pay 1, 2, 3. Three swapping to get to the front. Okay. So you pay in total 7 units. 7 unit of cost. All right. So that is when you do 22. Now the next, when you search for 22 again, you pay what? 1. You only pay 1 because this one you pay 7 unit of cost. All right. But because you have moved 22 to front, so you're paying 1 unit. Then you save a lot already. Okay. Next, you search for 11. 11 is now here, right? You pay 1, 2, 3, 4, and then 5, 6, 7. Again, you move 11 to the front and you pay 7 units. Okay. 7 units. Okay. Cost. Okay. All right, then you search for 15, maybe. All right, you search 1, 2, 3, 4, 5. 15, then you have to move 15 to the front. 6, 7, 8, 9. All right, so you pay 9. Here, 9 units. All right, 9 units, and then this one, only 1 unit. You found it already. Okay, and this one, you do it, 18, where is 18? 18 is at the back. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this one, you got no choice to pay 11 units. All right. So now the claim is that this is good. This is a very good strategy. Why? Because this strategy can be, of course, if somebody has the hindsight, he can see everything beforehand. This somebody we call him superhuman. Actually, I use the word God here. Maybe not appropriate, so I will not use it. I will use superhuman. All right, so how do you know that this is a good strategy? So you would have to compare what you do. So in here, I pay 7, 8, 15, 15, 20, 24, 25, 35, 36. So in doing this, I pay 36 units in total. Okay, maybe there are some more to add. Okay, all right, and then you sum up all these units. Okay, and who to compare? We compare with the superhuman. All right, that superhuman able to do it offline, meaning that superhuman, all right, which is the god, that it can do it offline by meaning what? This guy is given, okay, the first search is going to be 22. The next search is 22. The next search is 11. The next search is 15. Next search is 15. Next search is 18. So given all these, you go ahead and arrange this guy cleverly. All right, because you're superhuman, so you know how to arrange this thing superly good for yourself. All right, so that you can cut the total cost in terms of the units. Okay, of course, we cannot claim that what we do here is the best, but we can say that what we are doing here is no worse than 4 times. This is the claim. This is a very interesting thing. If you're interested, you can read this guy, this particular paper, which I had it afterward. I'll show you. All right, basically, what we are doing, it's called online, on the fly. We only get the info about searching 15 at that moment, at time 1, 2, 3, 4. Okay. At time 5, we only know that we get search 15. At time 18, 6, we only know we're searching 18. So we are doing it online on the fly, responding to the work on the spot. On the other hand, this superhuman, he is not doing it online. He's doing it offline. All right, meaning that he can do the best in the world. All right, basically he can play magic and then do whatever he wants, and to suit this particular searching manner. And so he is doing it offline, and we are doing it online. And the claim is that, okay, no matter how superhuman you are, I am a human. I only do at most four times worse than you. Why is this four times worse is any significant? This four is actually a constant. It's as you know, I'm only four times worse than you. No, I don't need to play magic. I don't need to know everything in the world before I can start doing things. I can do things immediately, and then I only be worse by four times only, which means that if my computer is four times faster, I already not worse than you in some way. Okay, so this constant loss, it's insignificant, and you are actually doing a very simplistic, a simple strategy that mimicking something like what you are doing already in life, and yet you are doing only that much worse than the superhuman. All right, so this is a very unusual thing in computer science. A lot of this kind of stuff are there, and they are all very beautiful. And using math, you can explain some of this stuff. All right, I really encourage you, if you're really super excited about this kind of stuff, you should take a look. This is only two-page proof. All right, the number is 4. Okay, so just two-page, but very dense, the proof. All right, so let me quickly sum up what I have talked about today. All right, what you need to do is that, in the coming years, when you study computer science, especially those of you who are in CS or IS, you will have encountered many of the subjects, and you should ponder a little bit what happened in real life and is actually mimicking in computer. Of course, AI is mimicking what is in real life, hopefully. But hallucination can you don't believe everything. Okay. So computer science is algorithm and data structure. From the beginning of this class, we talk about algorithm, and then here we talk about data structure, and subsequently you talk about paradigm. Actually, it's coming like the dynamic programming and memorization. Okay. And the next point is that computer actually is developed in a layer by layer. This is a very interesting. This is a segregation of responsibilities from one layer to the next. And if you stick to this layer by layer, you will not have to worry that somebody who developed the lower layer changes it, but your system will not have to actually change still because you are using the API to interface. Now, halving and doubling, it happen very often. You saw this halving. This is doubling, 16 to 32, 32 to 64, 64 to 128. All right, and this kind of thing happen very often. And last but not least, we are actually doing things managing complexity in this course. There are lots of things that, but if you can do how to manage, divide and conquer by what wishful thinking, things like this, you are actually managing how complexity to do computational thinking. Okay, I'm done with this, and any question? We can leave all the question about midterm later on in the during the proper session. Anything in the discussion of review, it's not officially and in your study, but I hope that you don't just study for the sake of getting good grades. You should see with keen interest that things that presented here are actually giving you a better view of things that are coming. Anything? If no, then give me a check. We take a break of about 7 minutes and then we come back. Okay, we come back at 8 o'clock. All right. We talk about a little bit about the midterm after. Okay, let me pause the recording. All right, 8 o'clock. Let's get started. A quick talk a little bit about the midterm exam. So here it's the seating arrangement. So they are the venue for yours. So this it's SR1 level 2. So for most of you, SR1 level 2 it's Com 1, the main building. Level 2, and you SR1 is here. There's the big seminar room. And then this one is SR3, which is this one next to it, just across the road. Right, and there's one in the VC room here. Right, so these are the three places that you will be sitting. You will have seat will have number, and you sit according to your number. All right. Then the page one of the paper looks like this. There are three questions. Question one has many parts. This one is a small question. So somebody asked about any method mark. Generally, no. There's no method mark that we can give you. Maybe with some minor exceptions of the typo that if we see in your method that it is somehow you work and then there's a typo that when you put down the answers. Okay. So be careful. Whatever you do, you have to. You can use pencil if you want to. All right, here we say because you're writing program, it's good to use pencil, but be sure that you do it legibly, and also you put in the proper indentation, so that to avoid any misunderstanding. I don't understand what is error carry forward mark. Right. If there are multiple parts, unless the parts are the part A and part B, usually they are all related in a way. So A will be an easier one, and then B will be a slightly harder, and so on. All right. This is an open book exam. You are not supposed to bring in your mobile phone will have to be turned off. There's no laptop. All right. If you want draft paper, you have to bring your own paper. You can bring everything you can have except for electronic devices. All right. So we print 8 pages for you. They are all together 8 pages in 3 questions, single-sided. So the other side you can use it as draft paper. All right. That's pretty much it. You only fill in your number here. All right, and this is open book exam, and there are some FAQ here. You can see it. They are all just, I guess these are almost understandable. Can I bring calculator? No. All right, so you don't need. You should be able to do simple multiplication and so on. All right, for those with MC, hopefully no. You have to submit it by noon, 20 by that day, the noon. And so far for number two, any official letters from NS by 21st of March. Now it's already 14, so it's by next Monday. If I don't get it, means this is out. All right, and also you have to be. I have to be sure that I'm sure that all these things means because if you are in NS, then you can do this. Any other events is not endorsed by us. There's no such thing that you can, because of that, you can take a re-exam. No. All right. We only honored things that related to your profession, which is if you are NS. If you are working, there's nothing, that it's also out of the question. All right. It's only NS that we were honored. Okay. Any other question? Yeah, okay. Give me a check. All right. Okay. As long as you have been following me and the TA on the recitation and tutorial, and also, of course, the review are good to give you a good picture, very big picture, and sometimes it may help with your study. and hopefully always, not just sometimes. So if you need to review my videos and the TA's video, and you can play it at 1.5 times the speed because I speak on myself when I view my old video. I feel that also I'm talking too slowly. Maybe because we're so used to YouTube nowadays that the speed it has to be accelerated to make it comfortable. All right, that's all about the midterm. We can now go back to our recitation. So this is number 5. Oh, by the way, this is lecture 1 to lecture 8 for the scope of your test and include recitation number 1 to number 5. That means this one. And tutorial number 1 to number 5. And also be careful that there are also concepts in sequences in lecture 7 and 8. And these are not it's another recitation. So if you want, you can do another recitation, number 6, to cover some of this stuff here. Otherwise, officially, we are until recitation 5. But concept-wise, we are allowed to test you on lecture 7 and lecture 8, which include the list, dictionary, tree, and so on. All right, so for our recitation number 5, it's working with sequence. So here are some notes that you have to take care of. Equality testing, there are 2 types, right? One is just in terms of number. The other one is. That means it's identical. Okay. Meaning that the 2 objects are identical, meaning that they are at the same location. So this one, I was testing it. This is Python 3.11. If you have a list, which is 1, 2, another list also 1, 2, okay? Then A is here and B is here. They are different. Right? If you print A is B or not, it will return you false because they are different object. Okay. On the other hand, if you C is 1, 2, D is 1, 2, this is a tuple, this is a tuple, and somehow the system put the 2 guys together here. All right. It makes sense that because list is mutable, well, so when you change one, you don't want to affect the other. On the other hand, tuple is not mutable, so if you change it, of course, it will be separated out. So, for example, if you change D to be 1, 2, 3, then right here. So when you print it, you print out the true. C is actually D. When D is switched there, so actually C will still maintain and D is switched. Okay, so it doesn't affect it. On the other hand, if list is the one, if you, both of them are pointing to the same list, changing one will affect the other. This will be the side effect. All right, so it's not. Okay, having said this, actually, when you change this to 3.6, actually, this is a little bit unfortunate to me that when you're 3.6, right, this is a tuple, this is a tuple, but they are different. Okay, so in this case, the result is that C is and it's not the same as D. All right, so it's false. Okay, this is because it's Python earlier version, and in this earlier version, it didn't optimize to put the 2 together. All right, so we will see this question afterward that this is actually designed for Python 3.6. I have changed this right up to include that this is for Python 3.6. Then it will behave in this manner. All right, so that it's the difference between equality and equivalence and is, which is identical. Membership testing, it's X in Y. It's true if X contained in the sequence type Y. Otherwise, it's not. And then the range type, you have to be careful. There are 2 ways to write it. Actually 3 ways in a way. So you can have a start and a stop. Okay. In this case, the optional stepping that you can have. So there are 1 way and 2 ways. And then this is another way. You just spell out the stop. So there are 3 ways in total. All right. The The difference of the range is that it's a range object is the way to make a small memory location to be able to represent 1 to 1 million, for example. You can use just a simple object to indicate that. All right, it's a small memory. Unlike you could have used the tupper for that purpose. But range is the one that can save you storage and you can use it. Next week, when I do my review, I will give you an example of range versus the map. Because the range is it's always there, whereas the map is not. Sometimes it's there and then it's gone once you use it up. Okay, so we are now ready to do question number 1. So let's see question number 1 here. Okay, Lee Su Min.
Hello.
Hi. Okay, let's do this guy together.
Okay.
Okay, so X is this, A is this. So this is, you see, this is Python 3.11.
Yep.
This is 1.2, this is 1.2. So what would you see for A? The A will be pointing there, right?
Uh, yeah, should be, yeah.
Yeah, see. Now B is X 3, 4. So B is also pointing to the same 1, 2.
Yeah. 1, 2, yeah.
Okay. So C is this. So C has this X in there and 3,
Yep.
4. So these 3, 4, 3, 4, 3, 4, they are the same collectively. They are the same, right? So okay, so there are 3 guys pointing to this 3, 4. Okay, so let's take a quick look. This one, if it's 3.6, you see that this 1, 2, it's
Oh,
duplicated here, and then but this is X, right? So this guy will be pointing there, right? So this guy is pointing there, and the 3, 4 is 3, 4, so they are not together. And this other 3, 4 is another 3, 4. Okay, so do you see the difference? So now X in A under 3.6, X and A,
should be false.
uh, X in A, which is true, right? What is
Is
in?
it?
A membership. It's membership, so it's true, right? True.
Oh,
Okay. This is X in A. X is A0. X is A0.
yeah.
No,
No? Oh, yeah, no, it's not. It's false.
it's not. It is false. This is 3.6. So
Oh,
for our purpose, usually it's 3.11. Officially, we use 3.11. So X in A is true. X is this is true. Okay.
mm,
X in B, of course, X is in B.
yeah.
X in C,
Uh, I think that should be false for now.
Y.
Because X is inside what's it, nested.
Yeah. So X is not in the
Yeah.
X is
C
not a member
itself.
of C.
Yeah.
You're talking about membership. Membership. Okay, we're talking about membership. So this is false.
Yep.
What is this?
Mm.
What is this? 2 plus 1.
Oh, I'm not sure.
They can guess. This can be guessed, right? What's true? It's 2, right? 1
Oh,
plus. What is this?
then is it two as well?
Yeah. Okay, so this is called promotion. Promotion of the type. All right. Boolean can be promoted to integer. In this case, Boolean is promoted to integer. It's true become 1, and 1 plus 1 is 2. So likewise, if you have a force plus 6, okay, so this is a promotion of force to be an integer, you will get what?
6.
Yeah, because it's promoted to 0, right?
Yeah.
Okay, you get 6. Okay. Okay, let's try another guy. Cohen Lim.
Yeah. Hello.
Okay. All right, so this is question number 1 here. This should be easy, huh? 1 equal to 1.
True.
True. If it is 3.6,
Uh, also true.
why? Let's see. Here is true. Okay, 3.6. True or false?
True.
True. Okay. 1 is 1. Okay. 1,
Yeah.
of course, is equal to 1. Okay. 1 is 1.
Uh,
What is returned true if two objects are identical?
true.
True. In 3.6, they tend to put into different place. You see different place. Is it going to be true? Is means identical. Okay, it's true. Because 1 is 1. One is a primitive type and there's only one. So they are identical. Okay. It's not an object and in a way. Okay, next one. Full equal to full.
True.
True. Because it's a same string, okay? String of double quoted or string of single quoted. This one,
False.
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 False, okay, because 0 is not the same as, okay. False equal to false.
True.
True. False equal to 0.
False.
Huh?
I mean,
False equal to 0, false.
true.
True. True equal to 1.
True.
True. True equal to 6.
True.
No, 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 no. True is promoted to 1.
Oh, yeah.
1, the same as 6. No, right? False. It's 3.6. Just want to be sure. True promoted to 1. 1 is not the 6. Okay. Next. 1, 2, 1, 2.
False.
False.
In 3.11, it's true.
True.
True. True. False.
Yeah, because this 1, 2, 3, 4, 5 is 1, 2, 3, 5, 4. Okay. Okay, next. This one, this one, this one. X is in S is Y. 3.11. Okay, by the way, this kind of depending on version, I shouldn't be testing you in the formal test. And of course, anything that we mark wrongly or mark that you can contest our marking. We are very liberal. We just give it back to you and you can contest. You can do that for midterm and also practical exam. But unfortunately, we don't have time for the final exam. Final exam is on Friday and marking the score has to be submitted by Monday. So there's no way you can check. But you can pay $10 subsequently if you want to look at the paper with administration. Okay. X is Y. X is Y
Uh,
is true.
this version is true.
11. True. X equal
Uh,
to 1. Of
True.
course. True. X is Z.
True.
True. 3 in there.
True.
True. One, two,
False.
1, 2. There's 1, 2 here. Why?
Oh, is it false?
Yeah, it's false because this is a tuple.
Yeah,
This tuple doesn't appear here. Okay, so this is false.
true.
Huh?
I mean, sorry, wait, yeah, it's true.
True, because this bracket is useless now. This
Yeah.
is a 2.
True.
Yeah, empty tuple is the same as empty tuple.
True.
True. 1 is the same as 1.
False.
False. This is a 1 tuple is different from 1. 1, 2, 3, 4. X in A.
True.
True. How come we keep getting this one? Okay. X in B.
True.
True. This one.
False.
False. Okay, we're done with question 1. Okay, for question 2, here you're supposed to write 2 functions, contains and also deep contains. So this guy is assuming version 3.6. So 1, 2 inside here for A, this is false. But for B is true. This can only happen if this question is casted in 3.6, Python version 3.6. Okay, let's assume it is. So can I see in the chat box what you have in mind? And then we can then work from there. Okay, let's see something. All right, contain for item. Okay, so this is iterative. Okay, iterative. Can I see any recursion? Okay, it's iterative again. Okay, so iterative seems to be the norm for you. So let me get the iterative. Okay, iterative. Right. So for item in tuple, tuple is the one. If item is the object, return true. Otherwise, at the end of it, you return false. Okay. So question is, what is the time here? What is the time and space? What's the time and space? Anyone? Okay, ON time and O1 space. Okay, got wind. Why? ON times.
Yeah, Prof, because in the worst case, right, you will have to iterate through the entire list to find whether the value
Yeah.
is inside the tuple.
Okay, so what is N?
And, oh, sorry, where n is the number of elements inside the tuple.
N is the length then, huh? Is it?
Yes, the length of the tuple.
Okay. And the space, why is it O1?
Because there's no deferred operations and there's no additional space used to create a new tuple. So the space does not change proportionally to the input n.
Okay, let's see. All right, I always wanted to try this kind of thing with this funny stuff. Okay, let's try with this funny stuff and see what happens. Okay, let's see. All right, so the simple stuff like this, you can easily you can get this, but I don't know. What is the length of this guy, Goldwyn?
Well, a bit hard to see, Prof.
Yeah, hard to see.
Yeah.
Hey, hello. It's easy to see.
Oh,
This is
sorry,
one, two,
five, five.
three. Ah, what?
The length of
Five,
the
right?
top itself is 5. So,
Yeah. I don't know why I have an extra comma here. It doesn't give me error. But it's okay. Let's try. Oh. Oh, I have a 6 here. So 1, 2, 3, 4, 5. Okay, so this is how it looks like. Now we go in there. Now you come to here. Yeah, even if you come to here, you one round only counting, nothing, right? So it doesn't cost. So you see that it's O of 1, and the time is O of n because 5 we just go through 5 rounds. That's it, right? So this is correct. Let me see recursion. Okay, I see. Okay, I see one recursion. Very young. Any more? Can I see others? Tuple 0 is object or something. Yeah, okay. Okay. Any more? Anyone else? So basically what Ray Yang you wrote down there, it's a summary of the two things. Okay. Recursion. Recursive here. All right. So if the tuple is empty, you return false. Otherwise, you check whether the first guy is the tuple. The first element in the tuple, is it the object you're looking for? If yes, it's true. Otherwise, you return recursively this. So Ray Yang, what is the time complexity?
Uh, wait, I forgot yesterday already.
Yesterday.
Wait, is it like n squared or
Yeah, this is n squared. What is n?
uh the number of elements or yeah, I'm not sure. Wait.
It's
Oh,
the
yes.
length of the tuple. Okay. And what about space?
Um, is it on?
No, you don't just say is it or is it not. You have to reason it out. So
Um,
what do you see in here? You see in here there's a slicing thing. All right. So something like that it's happening
or n
and
squared. Wait.
square. Okay, let's check it out. All right, we have to be confident, huh? Okay, let's check it out with line 40. Line 40. Okay, so this is our tuple 5. So if we go into the loop, see what happened. You see the slicing 1, 2, 3, 4 become 2, 3, 4, and then 3, 4, and then 4. So these are stacking up of the memory, and this is the length. 5 items, 4 items, 3, 2, 1. All right, so this is a proof that this is n square space. And because this is n square space, you cannot run away from n square time. All right, so we indeed needed to spend the n square. On the other hand, this long chain of tuple, which looks like this, doesn't affect the time at all and the space because it's simply pointers pointing to it and it doesn't get copy. All right, so indeed, n is the length of the tuple, and time is O(n) squared, space is O(n) squared. Okay. All right, so this is content. Next is deep contents. What is deep contents? Deep content is to dig into as deep as you can. So, for example, X is inside, this inside, so you can output true. Even though content X is not contained in A, but is deep contains in A. It's true. So can I see your code? Oh. All right, so I see you use is instant to check whether this is the construct you needed, or you use the type. All right, so there are two ways you can do it with the instance, is instance, or you use the type to help you to check. Okay, it looks okay. Got win. I'm not so sure yours is going to be working or not. Oh, you are using a iterative. If type for E in A, if type E is the tuple and E is and not E is X. What is E is X?
Yeah,
Oh, you
because I
check.
just want to catch a situation whereby if, let's say, X is a tuple, right, which in this case it is, I don't want the code to mistakenly call the recursion when it already found the situation. So I must catch the case where they see that the element is a tuple and they make sure that the element is not the object that I want to identify. And if that's the case, then I call the recursion. If
But
not, then
if
you
it
check
is
manually.
what, so you check with else if E is in X, then you do it. Oh, I see. But it's deep contains.
Yeah, I think I could have written it in a more optimized manner, Prof.
You may want to check this carefully. I'm going to give you one thing, which I know it's going to be wrong. So you will see this discussion at case A, all right, afterward, to know that why yours is in danger. What you do here is you return deep contents directly, and you never check the rest of the. You never check the rest. Oh, because you are using iteration, so you only do that one. Okay, maybe you're okay. I'm going to show you the various cases here afterward. Okay, let me just see others. Okay, so all right, so let me just give you my. First of all, I give you recursion. It's iterative. Oh, I haven't done anything here. So this one. All right, so if tuple is empty, you return false. That means that you have nothing to check against for your object. If otherwise your tuple is not empty, you check the first guy. Is it the same as your object? Which Godwin has checked it in the other more convoluted way to me. Then you return true. Else, if the type of the tuple 0 is a tuple, and this deep contain, then you check that if it is a tuple, then you have to recursively do it for this particular item element type 0. And if it is true, then you return true. Else, return deep contain this. Okay, so let's comment out this one. And try out. Try out these 5 cases. 1, 2, 3, 4, 5 cases. Right, in the first case, 1, 2 is there, the X is there. Right, I put X explicitly because I'm doing 3.6. So if I do 3.11, then this will still work. And 1, 2, X is there. So everything is to be true. 1, 2, this X is there, so it should be true. This one, this case should be true. Should be true. Let's see. All right, everything is true. Okay, let me just make it false. By making it false, I mean my A should be without the X. B is without the X. C is this. D is this. Okay. So all are false. Okay. So let me put it back. All the 5 cases. Okay, maybe just this case. This case will do. I just want to see this case. And I want to change my code a little bit to show you that this seems to be correct, but yet it is wrong. So this is the code. If I do it like this, all right. So this code looks as if it's similar to just now the one, but this is wrong. So let me run it. Oh, 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 let's go Poland. What? Ah, this is what? Okay, the first one is false. Supposed to be true, but it's false. All right, so the code is wrong. Now the code is wrong. Let me just put it back. The code should be N and return true. Right, now let's see how much time is it. So Godwin, we were on this. How much time do you think this is?
Wait, should be n square,
What is N?
where n is the length of the tuple.
What is the length of the tuple? If I have this,
It would be 5.
it will be 5. Okay, let's see, huh? Let's trace line 59. Line 59, okay. Okay, observe what is the changes here. Of course, you cannot, we just quickly run through it. So you see this. Okay, any few? Godwin?
Yeah, it will be more than 5. You also go through all the
Mm,
tuples.
yeah. Okay, so this n is wrong. This n is not the length.
You
All
can
right,
see that
it
it's
actually,
the length of the main tuple and the combined length of all the nested tuples.
yeah,
It's better.
yeah. So I will count the number of nesting. Okay, so this n is not the n that we usually talk about. So you always have to remember that there's such kind of peculiarity that things are empty, empty, empty until the last guy. So n here is the total number of items in all the nesting of tuple. Something like that, huh? Okay. What about space?
Space should be ON.
O of n. But didn't you see just now? It's more than O of n, right?
Wait,
59. You see, this one is n squared here, right? What else? All right, it's quite safe to say that this is also O n squared, but n is the total number of items in all the nesting. Okay? All right.
Okay,
This a little bit over, but it allows us to have this flexibility. Okay, so this is the recursion. Iterative. I think I saw some. Yeah, Yuan Yi Tan. Yuan Xu Tan. Okay, Chen He Lim Chen He. All right, so let me just paste it for you. Okay, so here deep contain for item in the tuple one by one. If the item is the same as that, return true. Else, the type of the item or its instance of, right? You can change this to be instance of. It's actually a tuple. Then, if deep contain of that it's true, then you return true. I put down here return deep content is wrong. I'm not so sure. All right, so let's work with this. After we can change this. The 5 cases. So this, so forget about this first. The 5 cases here. X, this one should be true. 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 And this should be true. It's 3.11. Okay. Okay, they are all correct, at least by example. So let's change this to return this and remove this to see what happens. This becomes false. All right, so the code is wrong. So this is wrong, but it looks like as if it's correct. Return this one is wrong. Why? Because when you say return, whatever this guy found out, you will return to the main routine. On the other hand, this code below, you only return if it is true. Otherwise, you will continue with the next item. Okay, so this is the correct one. Okay. Same thing. We want to see what happens if it is this kind of funny structure. Line 76. Let's see. It looks like this. Want to go in and see how? Okay, got some sense. Okay. Okay. 79. Yeah. So what is the time and space complexity? Lim Chen-he.
Hello, Prof.
Yeah. What is the time and space?
For the recursive, the iterative one below, right?
Yeah.
It should be O(n) square.
Square.
Yeah.
Time. Then you
Yes.
have too much already.
Sorry?
Let's see. Too much. Let's see this again. Look carefully, Line 79. Here. Okay. You have this picture. Now you go in there for item. So you take the first item, you check. Not true. Eject is not a tuple. Go down. Go to the next item. Right. Second item. Check, not true. No. Take the third item. Third item. Not true. Take the fourth item. Not true. Take the fifth item, which is this object. Is this one? No. Type is a tuple. This is true. So you go into here. If deep contains this, so you go through one by one.
Yeah.
Okay, so what is the time?
O(n).
What is n?
N is the length of the tuple.
The length of the tuple? What is the length of the tuple? 1, 2, 3, 4, 5.
No. Sorry.
Mm.
Should be the let's see.
Should be something like this.
Yeah. The
Okay.
nesting of the tuples.
Okay.
Yep.
What about space?
Space should be O(n) also. And the same n.
Okay. All right. So sometimes we can be fooled by ourselves. If you don't see this kind of structure, you have to try this kind of structure to be sure we don't get fooled by the system, by our own understanding. Okay, so that is question number 3. Number 2, we are done. Okay, so let's go to number 3. Number 3 here. So number 3, yesterday I did it and it got very confusing after a while. So let's I did do this thing before with you. This is a folding thing. It's a fold left. It's a fold right. All right. And actually, when you expand out, and today I posted it in the forum. Oh, not in here. The forum. Recitation and tutorial. Okay. Here. All right. So accumulate, it's actually resulted in this thing. Okay. This is equation 1. Meaning that you take the first item, work with the result of the rest. So if you look at it, it should be taking the last item, work with the initial thing, then work with the second item with the result, and so on until the first item. So this guy is from the back to the front. On the other hand, fold left, this is fold right. This fold left is doing it as if you expand it out. Expand it out means you look at this code, you trace it out, you will see that you will have to do recursive till end the second last item. The function is this function. This function is this represented with a cross with the last guy. And then you will expand this out, you will be the last guy with the second last guy, then the in front. If you work on it all the way, it become last guy, second last guy, and so on. As a result, you are actually doing the initial with the first guy, and then the result with the second guy, and so on. So this is from the front to the back. This is from the back to the front. All right. So this is what I mean. So accumulate, it's seeing the last one come first, and if you do this, accumulate is the last one, then this second last one, then the third last one, and so on. And this is the initial. So it looks like this. So we see the last column first. All right. And y, this is a function. Y is the value coming from 1. And the first number is 4. So 4 times 1 to give you 4. And this 4 take with the 3 to give you 12. The 12 take with the 2 to give you 24. 24 with 1 to give you 24 answer. So the answer is 24. Okay. So this is how you do it. Of course, you can take it and trace it faithfully, but that will cost you a lot of time. Usually, we want to get the semantic of the higher order function, and then we can quickly list down the answer. That is always the aim. Hopefully, there is a meaning to this guy. The meaning of this guy is from the back to the front, and you can list it down like that. Okay. Of course, you can also do it explicitly with this kind of equation, right? But in assessments and so on, you don't have time for this kind of stuff. Once you understood what it is, and then you just have to apply it in this manner to get your answer. And full right, it's going to be the same as accumulate. So you would expect that this part is the same as what I put down just now. It's the same. And the answer is also 24. Okay. On the other hand, for full left, you saw just now this discussion, it's from full left is from the front all the way to the back. All right, the first guy with the initial. So in this case, the first guy with the initial is this, the first guy is 1. So 1 times 1, because it's a multiply. You get 1 first and so on. And so this is what you have. All right, so let's see. Until line 46, we should get 24, 24, 24. Yeah. 24, 24. And 24. Okay, so this is what it is. All right, so now that you understand this, then it'll be easier to do this with a new function. So this pair is a function, divide is another function. So we want to do it with divide for full right. Full right, we remember it's from the back to the front. So the back work with the back is 3, work with the initial, so you get 3 divided by 1. Okay, and this result is going to work with the 2, and the 2 is going to be in front, 2, and then the result is 3 divided by 1, 2, and then 3 divided by 1. And then this whole thing is going to work with the 1, so the 1 is divided with this. Okay, and so this is the answer. So let's see what is this answer. This is 1.5. Okay, so we expect number line 60 to give me 1.5. What about this guy? This is 4, 3, 2, 1, 4 right. So you can, so the first guy is 4. Then this one is, of course, you can again go and trace it faithfully, but I don't think we have the patience to do that usually. Right, this is the quickest. Once you understand the pattern, then you do this. And then take it from here. And then the last one. And so this is your answer. What is this? Oh, missing one. 0.375. Let's check. Line 65. Yeah. And here. This one is 1.5. This one is 0.375. 1.5. 0.375. So we are correct. Okay, so the same for the other one. So now it's divide with 4 left. 4 left, we remember is from 1, 2, 3. Okay, so and the y is the initial is here. The initial is at the back here. So this is the first one. So this should be 4 left, 4 left. Okay. Okay. 4 left. So it's the 1 divided by 1. Okay. This one is this one. This one is this one. And then the result it's divided by 2. this result is divided by 2. And then the result is divided by 3. Am I correct? Let's see. Huh? Unmatched. Okay, 0.1666. Line 71. Let's see. Oh, I should have clicked to the next one. Oh, 0.1666. So this is correct. And the next one is 1, 2, 3, 4. So it should be this answer with divide by 4. And this is oh, like 0.0411. Okay, so this is the answer for this guy. Just now maybe I make a mistake. So this one is this one. Oh, why? Because divide A is the initial, B is the number. The result divided by 2. Okay, you can figure it out by tracing it yourself also. All right, next one, even more bizarre. It's this one. Is the initial is this. So let me just don't torture ourselves. Let me just copy what I have for you. It looks like this. All right, so you take the from the back to the front, so the 3 form with him, then whatever form with the 2, whatever form with the 1. All right, so the next one is the same. 1, 2, 3, 4. So 4 first, then whatever form is with 3, then whatever form is with 2, whatever form is with 1. And then the 4 left, it's again the similar kind of stuff. All right, of course, let me say it again. You can always do it diligently, or you do what I did with knowing that 4 left means from the front to the back. 4 right means from the back to the front. Okay, so this is the answer. And this last one is this. Okay. All right, so that's all I have for you on this example. I added a 4 to make ourselves better understood. Okay, next, give a property that function should satisfy to guarantee that 4 right or accumulate is the same as 4 left when producing the same values for any sequence. Yesterday when I was doing this, I was a little bit puzzled why I need commutative. I posted it here. Commutative means A with B is the same as B work on A. Associativity means A work on BC is the same as A work with B, then with C. All right, so associativity and commutativity are both required to make sure that equation 1 and equation 2 have the same result. If the operator is such that it has both associativity and commutativity. Right, how does this work out? So if you do accumulate, you expand out, you see this thing. So the operation is the last one with the initial value all the way until the front. And while the full left is from the beginning with the initial, so initial is here, the beginning, the first one is here. So it was right that this one is the initial and this one is the first item. Therefore, this answer with the 2 is the second item. This answer with the 3 is the next guy. Okay, so once you expand out, you see equation 1. You expand out, you see equation 2. So the requirement is that you want both of them to have the same result. The first and foremost that you must have is that they both use the same initial. Okay. All right, we will the same initial value for both of them. All right, then you can talk about it. So once you have that, but you check that this equation and this equation, they are kind of different with different ways of parentheses. So I do step by step for you to see that equation 2 can be transformed to equation 1 if you have this property commutative. So from S initial with S0 can be swapped to become S0 with initial. All right, so this is by commutativity. And once you have done that, this parenthesis of these two with this guy can be reparenthesized with initial with S1, so by associativity. Right, so meaning that instead of doing this, then this, I can do this first, then this guy. All right, in doing so, I reach the second line. Then I swap these two with commutativity again. Then you keep doing this thing. You will get to this guy, which is equation 1. So equation 2 and equation 1 are the same when you can do commutativity and associativity recursively, or I mean interleave. Right? Commutative, associativity, contributive, associative, and so on. Until the end, you get them the same. All right, so the answer for this is that they must have associativity and commutativity. And also, of course, the initial value is the same. All right, so this is for B. I didn't expect that this is the kind of argument. It took me a while to formalize this. This is exactly the kind of proof that if you do mathematics, this is exactly. We don't just state it without reasoning. Yesterday I was puzzled because I didn't have a reason for this guy. But after writing it down, I see that I have the reason to it because I need to use it. Here, need to swap to be able to use it. Okay, so there's B. Yeah, okay? Yeah, okay, give me a check. You can read this thing later on also. All right, for this week, besides this thing I posted, I actually posted another one. I posted the these things here. Are there any scenario in life that you notice the mimic design algorithm and data structure? All right, if you can think about it, you can post something here. All right, so this is question number 3. And let's go on to question number 4. Question number 4, you're supposed to design a data structure. So you see that Q It's a derived data structure. So we talk about that. We provided actually queue in Python is also available, if I remember correctly. Is it? Let's see. Oh yeah, it's there. Okay, queue is there. But this question is talking about not using the system queue. Yeah, you're using your own queue. So you're supposed to develop your queue. And queue meaning that is first in, first out. It's just like in real life. Again, you see that this is real life is being used in computer. We needed to implement this thing. You have two choices. One is the stack, or the other one, sorry, I mean tuple. The other one is the list. And of course, you know that tuple is not mutable, and so if you make changes to your queue every time you're paying or O of n time. On the other hand, if you are using a list, again, also the same. If you need to take out someone from the queue, which is the head of the queue, you are also paying for the linear time, the number of people in the queue. So that is also not quite desirable, but you have a way out if you know how. Okay, let me see what you have first, then I'll talk about it. Yesterday, I learned something from one of you guys. Okay, can I see what you have? How would you answer this thing? How do you implement the queue? Anyone? Oh, okay. So empty and queue is this, DQ is this. Uh, okay, so Bruce, you're using the tuple. Let me see. Wang Yanqing. Wow, why so complicated? Wang Yanqing, you there?
Oh yeah, this is just a interesting solution I saw lah. Because like, normally if you use a tuple, right, the time complexity will be O(n). But I saw that this solution, the time complexity is only O(1).
From where?
Yeah, the if you implement the DQ, right, you average out to O(1) because only when the out stack is empty, then you need to append to the out stack. Otherwise, you don't have to uh do the while loop. So like it averages out as faster.
Oh my God. This is can you explain the concept a little bit? So you have two stack, the in stack and the out stack.
Yeah.
Okay, so the in stack, out stack equal to Q. What does it mean?
Oh yeah, the queue is like the for the data structure is like queue is like a tuple of two lists.
Upper of
The
two.
one on the left is the in stack and the one on the right is the out stack.
Okay,
So like if you enqueue, right, you add it to the in stack, the list on the left.
okay,
So during the queue, right, you want first in, first out. So like at the start, right, the out stack will be empty. So you add in everything from the in stack to the out stack with this append function. And so the first one out from the out stack is dot pop. So you return the new queue.
I'm taking a picture just to check it out later. Okay, so your in stack, out stack is the Q. In stack dot append X, and then return in stack, out stack. Um, and DQ, Q is also in stack, out stack equal to Q. If not out stack. Where do you get this, huh?
Yeah, actually like my at first I type out the tuple answer, but then I asked like so online I saw like this solution.
Oh, okay. I will study this and I will see whether I can comment anything or not. For now, I'm a little bit blur with in stack, comma, out stack equal to Q. Can you enlighten us? What is this syntax? Huh? You can have two
Instead
things. Huh? How come you can
is
have
like
this?
a list lah. Like instead is one list, then outstack is another list.
Then equal to Q means what?
Like a queue is like
Okay, so but when I apply this fill function, apply this.
when I checked it, it works lah.
Oh, it works, huh? Okay. So when I do this, it works, huh? Is that what I mean?
Yeah, it should work lah.
Okay. And then what about the time complexity for each of this?
So it's like at the start it's like the DQ is like it'll be ON lah because like the outstack is like
Oh,
not
okay. Now
outstack.
okay, I see what it is now. Because you define empty queue, it's two lists. So when you put in stack, out stack equal to Q means that in stack is the first list, out stack is the second list. And then in stack dot append X, you are putting the item into the in stack. And then you return the in stack. Okay, now I understand. Then when you dequeue, you also say in stack is out stack is the all this first for convenience. So you just instead of calling it the first list, second list, you call it in stack, out stack. If not out stack, while in stack, out stack top append the in stack pop. When the out stack is not empty, is it? If not out stack, while in stack, then out stack equal to pop. You return this. This is DQ. How much time is this?
It'll be ON lah. But let's say if you call like multiple and queue,
Uh,
like then you'll become O1, average out to O1.
oh,
That's what I
is
saw.
it amortized or what?
Yeah.
Okay, I will check that. And Q hit instead of stack. If not out stack, well in stack. Okay. All right, so this is one possibility. I will check. The other one that yesterday someone gave was a double hit. Basically, he's a moving pointer. So as people add into the queue, the queue get increased, right? The end pointer, so you don't care actually. Then when you pop, you just move the head to one step ahead, and then you continue doing this. Maybe I will take yours together with this one and say something about it tomorrow and give it to you all. Otherwise, what I have here it's the standard, and which is a dumb thing. It's pretty dumb for this question. This is what I have. Okay. Empty queue is this. The NQ it's just to take the item, append it, and return it. So this is O of 1. The queue is simply pop it, return the queue. All right, and this is O of n because you got no choice. And this is already there. And then NQ is already here. Okay, sorry. Why I have too many of these? Okay, the head is simply take the head is O of 1. Oh, why I have another head? Okay, so just this. It's good enough. Let's see. Yeah, 565. All right, so this is a naive, simplistic one. All right, I'm using lists. Well, what we saw just now by Wang Yanqing, it's a sophisticated one. I will check. And yesterday also got one version which is using the head moving. And in doing so, actually, there are some garbage in the front, and the garbage should be collected. Otherwise, it will just be always there. Okay. Any other one has any other question on this? This is supposed to be a simple one, but it can also be complicated. All right, like Bruce one is the same as mine. Deepan is also same. Okay. That is question number 4. Question number 5, it's here. So you are told that X is this 1, 2, 3, 4, 5, 6, 7. How can you produce this, and so on? Okay, let's see. What do you have? Can you do A, B, C, D, and so on? So the A should be quite straightforward, right? Because this looks like 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square. All right, so you're supposed to use filter, accumulate, and map, or as discussed in lecture. But I don't have my map here. So, okay, so Godwin has this, which is correct. But if I using if I use this map, I don't have a map here. I using the system map, then I need to change it into tuple. All right, so let me try to show you. All right, this is the answer. Because I'm using the system map, if I forget about this tuple, then I get an object, which is not what we want. I get an object, map object. Okay, so if you have the map, if you have a map in this code, then you can use it. For me, I'm using the system map, which is giving me an object. All right, so I need to put a tuple there to move the object into tuple. Okay, B is 1357. So basically you're taking the odd number, 1357. The 246 is the one. So, and this is again, you see that mapping is to deal with things for every element. Filter is to select things that you want. Accumulate is to find some kind of statistics or summation of things. And these are the 3 operations. And the other 2 are the searching and sorting, which are not used here. So these 5 items are commonly used for processing big data. Okay, for B, I see. Okay, so the filter, it's all there. All right, so it looks like this. All right, the tuple, because filter is a system filter, unless you are using your own filter. For me, it's a system. If I forget about this tuple, I will get object. I get an filter object, which I don't want. I don't want tuple. Okay, 1357. Okay, what is C? Oh, this is just a pair. So this should be easy. So it's just using map. You have to decide, is it map or is it filter or is it accumulate? Clearly this is a map because you're mapping each one to get this. So you are encouraged to give many more versions of the answer. So this one, you're encouraged to provide multiple solutions for the above questions. So here is again the map to this. Could there be any other solution? Let's see. Using pair. Someone using pair. Okay. What about D? What is D? D is oh, this looks like the pair thing, 2, 4, 6. So which means that you only want 2, 4, 6. You don't want 1, 3, 5, 7. So this is an even number. So first of all, you have to get all the even number. So I have to get all the even number first. And this is my D, my even number first. So I'm using my XX. Then if I try my pair, do I have my pair here? Oh, my pair is here. My pair. Let's try what do I get. I get this, which is not quite correct, right? Because I got extra of this guy. It is this extra. So I supposed to get rid of this. So it should be some kind of condition that I can set. So by learning that, then now you know that this is no good. It shouldn't be just a simple pair. It should be doing the conditional pairing. All right, so here is the answer. All right. Oh, I have a full left. Yeah. Lambda AB. We only if A the initial one is this empty tuple. I don't want to pair him. I will just use him. Otherwise, I pair it. Okay, so this is my initial. This is my input XX here. So I have to get rid of the extra pairing, which is by this condition. And I should be done. Yeah. Okay. So this is how you can play with. You just put it in first and see what happens. If you need it, you just add condition. Likewise for this guy, so if you use the pair directly, you can't get it. So there's this in the tuple in here. So again, this is a condition. So it really looks like this guy, but this guy you make it into a pair, right? It looks like this instead of this, and the rest are the same. That is E. Okay, and then my F is maximum and G is minimum. Let's see. Oh, okay. Maximum minimum. So you can always write your own maximum minimum, or you can use a system maximum minimum. All right, so this accumulate by maximum among the three of them. It cannot be filtered. It just going through every single one to find. It cannot be map. Map is to take the value and map to something. It must be using accumulate with the maximum. Either you use a system maximum or you can write your own maximum. Right, this is your own maximum. AB, you take A if A is larger than B. Otherwise, you take B. The minimum is the same. You take A if A is less than B, or otherwise you take B. Right, so this is. Right, 7711. Right, 71. Next one is the maximum square even element of X, which means that you take out all the even number and square them. So first of all, you need filter. Secondly, you need to do mapping to get 2 to 4, 4 to 16, 6 to 36. So this is how it looks. And the I is, what is I? The sum of the square of each value in X. So you square, 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 and sum them out. So squaring is the map, summing is the accumulate. So that's it. All right, you square first, then you sum. So this is a signal processing way of doing things. So this is done. This result is packed into here as the result. And we are done. $36,140. Yeah. Okay. We are done. Any question? We are on time. All right. If you're okay, then we call it a day. And I owe you the question number 4 to look at the various way. There's some question on midterm. Can I see the code again and in the midterm? If this type of question is tested, will map filter accumulate be given, or is it the Python one? Or can I see the code again in the midterm with this type? Oh, yes. So I suppose your question is such that when there's a question about map, then you would understood that it is from the system. Then of course map you should understand it very clearly. As to accumulate, surely. Oh, sorry. I got a fright. When you have accumulate, this kind of thing will be given to you. Yes. So nothing to remember. All right. You're not supposed to remember any of this. Okay. If we need to test you on any of these higher order function, the code will be given to you. And of course, you also, it's an open book. You can always summarize this also in somewhere. But you cannot take it that full left in here is the same as the full left in the midterm, right? So you follow whatever is given to you in the explicitly in the paper, in the midterm paper. Okay. Does it answer you, Yuan Xu? Any more question? Or will we be forced to use iteration or recursion only in certain questions? Yes. All right, because I could be giving you a iterative one, and you're supposed to give me a recursive one. You cannot give me back the iterative, right?
Okay, yeah. I was talking about a specific question in like the practice lah. Cause like one of the question is like if
Yeah,
you
what?
one of the question is like where can't find the question right now.
Yes, can I also check which mission is with will the midterm be relevant until? Oh, which mission is relevant will be if you look at the deadline here, mission 6. Were we forced to use iteration? Yes. All right. So this is the timetable, and so mission 6, you should know until mission 6, 26th of March. Wang Yuanqing, your question I answer, right? You will be forced to use iterative or recursive. Yes.
So like if you're not like forced to use, then we are allowed to
Yes.
do
Correct.
whatever, right? Okay.
Yeah. Correct. If the question is not clear or not spelled it out, you are allowed to do whatever you can. Oh, you're deep fry. I don't know. No, what this is mean. 1 month behind. You're 1 month behind cannot be because this is the deadline we follow. Yeah. So anyway, as I said earlier, over and over again, you are after our marking, you get back the paper. You can always contest the marking. But the thing is that if you contest, you must be prepared that your contest can fail, right? Like those people who appeal in the high court, they may get even heavier sentence, right? So that possibility is there. Okay. The last question in the recitation just now, this one. Yeah, here. Any more? Okay, next week you still have another chance to ask. I will take the review, my last review, and you guys can ask. All right, as long as I emphasize this a lot, that you have been following what I talk about, my style is pretty casual. I like to relate to things, and I like you to think about making question yourself. Basically, when you see this, all right, you can go and think about it. What else can I ask? Or what else can you ask yourself? Right? And you can then pretty much learn about examiners' mentality, and you can then cook up questions that possibly that what the examiner may cook up. All right, nothing to worry about. And this it's a small test in a way. More importantly, you learn in this class. The grades can always come later. If you like it, then you keep it. If you don't like it, throw it away. Okay? All right, I guess that's all. Good night. Can I disclose how the bell curve moderation will be like? There is no bell curve here for one test. The bell curve will come at the end of the whole course. Okay? I don't go and check out percentage of people in this. It would come as naturally as a bell curve in a way, but I don't modify anything. I will just give you whatever grade you have. And at the end of the course, you guys will be put into a bell curve. Yes. There will be certain percentage of the people with A plus, A and A minus, and B plus, B, B minus, and so on. But majority of you should get at least a B and above, because it's the way that this course is conducted. Okay. Good night. Let's go. I still have work to do for you tomorrow. Bye-bye. I lock on now.